All right, welcome back. So this is going to be another video on mathematics for machine learning. So anyone who follows this channel knows that I've become a AI realist after reading Situational Awareness by Leopold Aschenbrenner. If you look back in history, the ChatGPT was released very recently. So when was ChatGPT released? So ChatGPT was released in 2022 as a model accessible through OpenAI's website. So since that time, there's been GPT-4 in March of 2023. And I think it's easy to forget just how limited it was at its first release. We didn't have image integration with it. We didn't have image generation integrated within the tool. We didn't have multimodal capabilities, analyzing screenshots, all that. It couldn't even integrate with browsing tools. So it really couldn't do much of anything. Last year and some change back, and then it was when it was first released in 2022. We had a GPT 3.5. It could just answer questions, generates text, and solve problems. So it really couldn't do that much. So the next question I have is, when was the GPT 3 model released? So now we wind back the clock even more. So 2022, the underlying technology behind ChatGPT was released. So we can see in just 4 years, we went from just only having the underlying technology to ChatGPT-3 to me now using it in place of Google for answering questions. Before this was released, I would probably have to go to Google to find the answers for these. So let's go to Google and see what I get. So we do get the right, a consistent answer, the right answer. And then let's see what happens when I go here. June 2022. So we do get consistent answers. It wouldn't be that bad to go to Google, but the fact that I'm using a different tool than Google is quite significant. So now let's ask it, when was the GPT-2 model released? So February 2019. So that's only a year before this the release of Dash 3. So the reason I became a AI realist is because you look at the trends, you look at the way it has increased since 2019. That's only been about 5 years, and look at how long we've gone. So the idea is that we're not at the pinnacle. We're not nearly. We're on a graph right now. I don't know if I do a paint. The graph is looking like that, right? And we have GPT-2 released very shortly after we have GPT-3 released. Now where we're at, where we have ChatGPT running on GPT-4, then we've got 4.0. So we're still not anywhere in this territory yet. So this is about 2027 here, and then all the way up through 2030, 2035. It's going to change the world, and this it's just going to continue to grow. And one of the ways it will grow is it will turn into a multi-trillion-dollar industry. So let's say so let's have a conversation about this. Okay, so tell me some major industries and their worth. For example, the healthcare industry. How much is that industry worth in the United States? And the manufacturing industry. I hope you understand what I'm getting at. If you don't, let me know and I will clarify. Make some estimates of the worth of an industry. For example, if I were to say that industry X were a multi-million-dollar industry, include industry X on the list with an estimate of its worth. So we're going to try to get a sense of other sorts of industries. So we see the hospital industry. Um, uh, yeah, so we've already got plenty of multi-trillion dollar industries. This is you know, thousand trillion industry. So this is the point, right? It's like the AI is going to be a similar level mature industry as like hospitals, commercial banking, pharmaceuticals, dealing cars. This is the point I'm trying to make. Okay, thank you. So basically the point I'm trying to make is that AI is going to morph into a multi-trillion dollar industry within 10 years. There are some typos, but the context should make it clear what I'm saying. So I'm trying to illustrate a point that AI is going to morph into a multi-trillion dollar industry, and that the idea of a multi-trillion dollar industry isn't like something that is unreal or just doesn't happen. Like, it's very realistic that artificial intelligence could become yet another multi-trillion dollar industry, because there already exist multi-trillion dollar industries, and the trend of the growth of AI, if you look at GPT-2 being released in 2019 and then what it's grown into today with only 5 years, it's really safe to assume a 2 order of magnitude growth or higher, which would make it unrecognizable to what it is today, in a similar way as GPT-4 and more sophisticated models are unimaginably more advanced than GPT-2. Yeah, so and we can see, not a lot of industries are multi-trillion dollars. So this takes a large chunk out of the percentage of US GDP. And then, in this list, and granted this is just a hallucination, these are estimates by the AI. Now we do have sources here, which is a new feature. It looks pretty cool. So yeah, we have yeah, so I think it's probably fair. I don't know what this number means. Yeah, I don't know what this number means. It because this is not a comma. This is a period. So, but we have trillion-dollar industries already, and then we have industries that are almost $1 trillion. So, it's not inconceivable to see AI becoming an industry with an estimated market size, that of hospitals, of public schools, of retirement and pension plans, property. It's really not inconceivable to imagine that, in my opinion. Yeah, so that brings me to the topic for this video, which is we're going to continue the mathematics for machine learning. So this is a book I got from reading a Reddit post, and it's a good one because it's it's in my documents. It's a good one because it's kind of designed for a broader audience. It's not a high level PhD college textbook. So, but even with its wider scope, I'm likely going to need to brush up on quite a few things. So I'll do a sound check in case none of this worked. I can scrap the video. Make sure my input is good. Yep. And let's try to make some progress. So linear algebra. When formalizing intuitive concepts, a common approach is to construct a set of objects, symbols, and a set of rules to manipulate these objects. This is known as an algebra. Linear algebra is the study of vectors and certain rules to manipulate vectors. The vectors many of us know from school are called geometric vectors, which are usually denoted by a small arrow above the letter. And then EG stands for example, IE stands for this means. So, for example, these are so that hopefully that'll look familiar. If that doesn't look familiar, you can use Khan Academy, but you know, we should all have a high school. Any you know, it's important that that's familiar. If it's not, you got a lot of catching up to do. In this book, we discuss more general concepts of vectors and use a bold letter to represent them. For example, X and Y. So that's a bold letter. In general, vectors are special objects that can be added together and multiplied by scalars to produce another object of the same kind. From an abstract mathematical viewpoint, any object that satisfies these two properties can be considered a vector. Here are some examples of such vector objects. Number 1, geometric vectors. This example of a vector may be familiar from high school mathematics and physics. Geometric vectors, see figure 2.1a, which we can see figure 2.1 is here, and then the left is A, the right is B. So on the left we have geometric vectors. Are directed segments which can be drawn at least in two dimensions. Yeah, so you can draw it in 2 dimensions. You can probably also simulate it. You could probably also get a VR application going for understanding it better in 3 dimensions. Okay, then we have 2 geometric vectors, so X and Y, which are geometric vectors. We know they are because of the symbol on top of them, the arrow. Can be added such that vector X plus vector Y equals vector C is another geometric vector. Furthermore, multiplication by a scalar, and that's lambda vector X, comma, lambda, and remember we have these bookmarked here, so let's make sure that we're not just glossing over these symbols because they're going to be important. So now we're talking about vectors, right? So so we're going to need to go to this section here that talks about vectors, and yep. So this part here talks about vectors. And it doesn't have any information about. Huh. I know I saw it I know I saw it before. Oh, here we go. So this actually does not stand for lambda. It stands for an eigenvalue or a Lagrange multiplier. So it's a multiplication symbol. And then, but it's a particular kind of multiplication. It's Lagrange multiplication, or it's an eigenvalue, whatever that means. I do not know. And then, so A is an element of set A. So that's what this symbol here means. And then we do have that that kind of R looking symbol. Yeah, here. So real and complex numbers, respectively. So R is a real number. So let's go back and look at what we got. Can advance the bookmark. Don't need that anymore. Oops. And it looks like I deleted the wrong bookmark here. But that's okay. I can get back to that pretty easily. Oh, it was a highlight. Oh, well, I wish I hadn't deleted my highlights. Yeah, I deleted all my highlights by accident. Oh, well, I guess that's a lesson to me not to use blue for my highlights. So I'll try to remember that going forward. If I use blue, then it's the same color as my bookmarks, and I'll make a mistake and delete them by accident. All right, so this stands for a real number as far as I know. Yeah, so it's a real number. So by scalar, this is also a geometric vector. In fact, it is the original vector scaled by an eigenvalue or Lagrange multiplier. Therefore, geometric vectors are instances of the vector concepts introduced previously. Interpreting vectors as geometric vectors enables us to use our intuitions about direction and magnitude to reason about mathematical operations. So next thing I'm going to do is something I think is really valuable. We live in the modern era, so let's use modern tools. So we're going to use ChatGPT. We're going to say rewrite the paragraph shown in the screenshot. Unpack all mathematical symbols shown into English words. Okay, so now we're going to reread this, and we're going to read it with everything all unpacked. So let's read the original one first. So the originally it says geometric vectors. This example of a vector may be familiar from high school mathematics and physics. Geometric vectors are directed segments which can be drawn at least in 2 dimensions. 2 geometric vectors, and we'll have those unpacked in English, can be added such that, and we'll have that unpacked in English, is another geometric vector. Furthermore, multiplication by a scalar, we'll have that unpacked, is also a geometric vector. In fact, it is the original vector scaled by, and that's the one of the key ones to have unpacked. Therefore, geometric vectors are instances of the vector concepts introduced previously. Interpreting vectors as geometric vectors enables us to use our intuitions about direction and magnitude to reason about mathematical operations. All right, so what is that if everything is written out into English? Geometric vectors are a type of vector that you might remember from high school mathematics and physics. They are directed segments which can be drawn in at least 2 dimensions. For example, consider 2 geometric variables, which we'll call x and y. You can add these 2 vectors, resulting in a third vector that we'll call z. In other words, adding vector x to vector y gives another geometric vector z. Additionally, you can multiply a vector by a scalar. A scalar is simply a real number, which we'll refer to as lambda. When you multiply a vector x by the scalar lambda, you get another geometric vector. This new vector is actually just a scaled version of the original vector x. It retains the same direction but has a different length or magnitude depending on the value of lambda. Therefore, geometric vectors fit into the broader concept of vectors as they allow operations like addition and scalar multiplication. By understanding vectors as geometric vectors, we can use our intuitions about direction and magnitude to help us make sense of mathematical operations. So I'm not sure how useful that was because I don't know if this was so was there anything. So let's say, what about eigen values and Lagrange multiplication? Don't the symbols unpack into something relating to that? In the passage you provided, the symbols and operations don't directly relate to those. Okay, well, interesting. All right, so let's keep going. So polynomials are also vectors. See figure 2.1.b. Two polynomials can be added together, which results in another polynomial, and they can be multiplied by a scalar, shown as such, shown as there, and the result is a polynomial as well. Therefore, polynomials are rather unusual instances of vectors. Note that polynomials are very different from geometric vectors. While geometric vectors are concrete drawings, polynomials are abstract concepts. However, they are both vectors in the sense previously described. So here's a polynomial. Now, a polynomial, let's get a quick, give me a really short and brief definition of a polynomial and show me an example. It's just a mathematical expression consisting of variables and constants. So you can't, yeah. So this is a polynomial. It's basically, because this is, if you know what x is, right? This would be a single number, right? It would be like for example, this polynomial. This is a polynomial here. So if x equals 5, now it can be a monomial because we know that it equals 8. But if we don't know the value of x, the only way to express it would be with multiple symbols representing numbers. So x represents the value that we don't know, and then 3 represents the value that we do know. So the only way to represent that, if we don't know the value of x, is as a polynomial. And I opened Copilot by accident. That's okay. All right, so number 3, audio signals are vectors. Audio signals are represented as a series of numbers. We can add audio signals together, and their sum is a new audio signal. If we scale an audio signal, we can also obtain an audio signal. Therefore, audio signals are a type of vector too. All right, and before we move on, let's get this unpacked as well. All right, so we'll take this. Okay, and then we'll take the next one. There we go. All right, and now we'll say, okay, now rewrite the 2-dot paragraph with all mathematical symbols unpacked into plain English. All right, so polynomials can be added together, and the result is also a polynomial. They can also be multiplied by a scalar, a real number, and the result will still be a polynomial. Because of this, polynomials are unusual examples of vectors. So if we have two polynomials here, the first one is x plus 1. Now we don't know the value of x, so we can't express it as a single number. We have to express it as a polynomial. And we have another polynomial here, and we can use that same unknown here. We could also do y if it's a different one. Let's go with y. So the second polynomial is y plus 1. So we can add these two polynomials together. All right, and that would be so they're added together, and now this is still a polynomial, and we can actually reduce this just by dropping the parentheses, so we get x plus y plus 2 would be the new polynomial here. And same thing for multiplication. And this is where it starts getting turning into real math. So you have to multiply each by each. So you start here, and multiply it. So it would be xy plus x plus y plus 1, and now the result is still a polynomial. So because of this, polynomials are unusual examples of vectors. It's important to note that polynomials are quite different from geometric vectors. While polynomial vectors can be visualized as drawings with arrows with a specific direction and length, polynomials are more abstract, existing as mathematical expressions. However, both geometric vectors and polynomials fit the definition of vectors as previously described. Okay, that's interesting. So how do you write a polynomial as a vector? All right, so you represent each term in the polynomial by its coefficient, treating these coefficients as components of a vector. So here we have a polynomial. We don't know what x is, so we can't just, if we knew that what x was, say x was 1, then we could write this as a single number rather than a polynomial, and it would be 10. We could just write it as 10 because we know what x equals, but since we don't, we have to write it out as a full polynomial. So you can write it in vector form by listing its coefficients as entries in a vector. So this is how you would do that. So 3, 2, and 5 would be placed like that. So here's a polynomial with a lot here. So, and you can't just write out polynomials in a random order. You have to preserve the order of polynomials, and we can see that makes sense here. If you wrote it in a random order, then there'd be no meaning behind this. So what are the rules for writing out the order of a polynomial? right, so here's the rules for that. It's based on the degree of each term. So descending order of powers, degree of the polynomial, terms with zero coefficients, positive and negative signs. So there we go. There are lots of rules. All right, and I have one last question for the AI, and that is, so this idea that polynomials are unusual examples of vectors, could you tell me more about that? Because as somebody learning this, I have no intuition for what is usual and what is unusual. Okay, so why are they unusual, and why do they feel different from more common or usual vectors? So a usual vector would be a geometric vector. They represent both magnitude, also or length and direction, and it's not necessarily length. It could be talking about audio waves. They exist in physical space in 2 or 3 dimensions. For example, the force of pushing an object or velocity of a moving car, they can be drawn as arrows pointing in specific directions. So you basically, it's unusual to work with a polynomial because you basically can't do any of that, is what I understand. So geometric vectors have a clear visual intuition. So if you roll a ball down a hill, it's clear you write a vector pointing in the direction that the ball is rolling. But polynomials are unusual because they're abstract rather than visual. If you roll a ball down a hill, okay, I get it now. So like a geometric vector, if you roll a ball down a hill, then you can easily visualize the vector because you can point it in the direction that the ball is rolling. So tell me more about a polynomial vector. Like, would that be used for rolling a ball down a hill? Can you give me like an example of why a polynomial vector couldn't be used for something that is intuitive, like rolling a ball down a hill? All right, and in the meantime, do that. So yeah, so abstract. Yeah, so like rolling a ball in the 4th dimension, like you probably use a polynomial vector for that. So yeah, so infinite dimension possibility. Yeah. Yeah, so it wouldn't point uphill or downhill. Okay, I think I get it. So it would be like rolling a ball in the 4th dimension would be something you'd have to use a polynomial vector for. Or like something like data. It's like, what is the trend in the data? You might have to use a polynomial vector for. So it's hard to like point and like intuitively think about data in the same sense you would think about as like geometric motion. Is that correct, or am I getting a bit off course? Yeah, so they're abstractions. They don't. Yeah. Yeah, I got it. So I'm on the right track. So if you're dealing with rolling a ball in the 4th dimension, then you'd likely need a polynomial or some other mathematical structure that is not as intuitive. That is pretty unusual. Yeah, and then data analysis. Yeah, so how stock prices change, over time. It goes up and it goes down, but it doesn't go up and down like a ball rolling down the hill. It does it in a more abstract way that would be perhaps represented by a polynomial. So you'd be thinking more about the change in direction or speed over time, which is something more unusual to think about than just a geometric vector. Just a car rolling down the road is a lot more intuitive than a stock price fluctuating at a different rate of change. Yeah, so there's more abstraction for polynomial vectors, so it's more unusual things that aren't really connected to the physical world, and therefore, yeah. Okay, so I'm happy with that. So moving on, and I already read this next one, so we'll go on to number 4. Number 4, elements of tuples of n real numbers are vectors. Tuples of n real numbers is more abstract than polynomials, and it is the concept we focus on in this book. For instance, and now this belongs to tuples of 3 real numbers, is an example of a triplet of numbers. Adding 2 vectors, a, b, as a set of tuples of n real numbers component-wise results in another vector, a plus b equals c, as a member of tuples of n real numbers. Moreover, multiplying a as a set of tuple of n by and we'll have it unpack it, results in a scaled vector as shown there, and we'll have it unpack it. Considering vectors as elements of that has an additional benefit that it loosely corresponds to arrays of real numbers in the computer. Many programming languages support array operations, which allow for convenient implementation of algorithms that involve vector operations. All right, and let's get this unpacked. Okay, great. Now unpack paragraph 4 in the screenshot. This time I want you to include a legend after unpacking that in LaTeX has the equation alongside the plain English it was unpacked to. All right, so I want to it to be more obvious how it was unpacked. All right, so oops, so it didn't do it properly. And it's kind of just failing now. Okay, you were close. I really like the legend. That was good. The thing that I would like to see done differently, though, is in the paragraph that is unpacked into plain English, I don't want any mathematical symbols at all in that paragraph. I only want the symbols to be shown in the legend, and I want the paragraph to be completely unpacked into plain English with no mathematical symbols. So now let's read this. So the elements of space called r to the power of n consist of order lists of n real numbers and are considered vectors. This space is even more abstract than polynomials, and it's the main concept that this book focuses on. For example, let's take a vector which we'll call A. This vector is represented as an ordered list containing the numbers 1, 2, and 3, and it belongs to the three-dimensional version of the space, often called r to the power of 3. This list of three numbers is known as a triplet because it contains exactly three components. When you add two vectors, such as A to another vector B, you can add each corresponding component one by one, resulting in a new vector, which we can call C. This new vector also belongs to the same space, r to the power of n. Furthermore, if you multiply a vector like A by a real number, which we'll call lambda, the outcome is a scaled version of the original vector. This scaled vector also belongs to the space r to the power of n, and I don't like how that was unpacked, so I will nitpick that. One advantage of considering vectors as elements of r to the power n is that it loosely resembles how arrays of real numbers are stored on a computer. Many programming languages support operations on arrays, which make it convenient to implement algorithms involving vector operations. So, I mean, the thing is, like, all right, so no, when you unpacked the symbol that appears as though it is the capital letter R to the power of n, I don't like how you unpacked that to the English phrase r to the power of n, because, like, that's not what it is, right? It's not a letter R. It's like a symbol representing something. So what I wanted you to do was unpack it to say, like, for example, the mathematical expression x to the power of n, I would unpack to plain English to mean an unknown variable raised to the power of any number. Yeah. So hopefully this is better now. Elements of the set of all ordered lists of real numbers with n components, there we go, that's what I'm looking for, are considered vectors. This set is more abstract than polynomials, and it's the main concept we focus on in this book. For example, let's consider a vector which we'll call A. This vector is represented as an ordered list containing the numbers 1, 2, and 3, and it belongs to the set of all ordered lists of real numbers with three components. Since this vector has three components, we refer to it as a triplet. When you add two vectors, such as A and another vector B, you add each corresponding component one by one, resulting in a new vector, which we can call C. This new vector also brings to the set of all ordered lists of real numbers with n components. Furthermore, if you multiply a vector like A by a real number, which we'll call lemma, the outcome is a scaled version of the original vector. This scaled vector also belongs to the set of all ordered lists of real numbers with n components. One advantage of considering vectors as elements of this set is that it closely resembles how arrays of real numbers are stored on a computer. Many programming languages support operations on arrays, which makes it convenient to implement algorithms involving vector operations. Okay. All right. Anyway, moving on. And let's read the side. So be careful to check whether array operations actually perform vector operations when implementing on a computer. Pavel Greenfield's series on linear algebra right there, and then Gilbert Strang's course on linear algebra there. 3 blue, 1 brown series on linear algebra. So yeah, lots of more sources to learn math exist nowadays than ever exist before in history. It is very, very easy to learn math. Much easier. Although the problem is, if you go to, um, especially if you go to 3Blue, 3Brown, now you're on YouTube, right? And like YouTube's going to try to get you to watch what it wants you to watch and doesn't care about what you want to watch, so it'll try to hijack your attention and pull you away from what you're intending to do. So in some sense, it's actually probably harder to learn mathematics than it ever has been throughout history, because your attention is constantly trying to be diverted away into advertisements. But let's just get these up on the board. I might include these in the description. All right, there we go. And now we also have another resource that wasn't mentioned in the book. I don't know if it wasn't mentioned because it's not a good resource, but we do have a linear algebra course in Khan Academy. All right, so moving on. So linear algebra focuses on the similarities between these vector concepts. We can add them together and multiply them by scalars. We will largely focus on vectors in shoot. I don't know how to unpack that. Since most algorithms in linear algebra are formulated in I need to learn how to unpack that. We will see in Chapter 8 that we often consider data to be represented as vectors in that. In this book, we will focus on finite dimensional vector spaces, in which case there is a one-to-one correspondence between any kind of vector and that, which we'll unpack. When it is convenient, we will use intuitions about geometric vectors and consider array-based algorithms. All right, so let's have it. Okay, so now, good. Now unpack this. All right, so rereading that with the symbols unpacked, we'll get linear algebra emphasizes the similarities between different types of vectors. In linear algebra, we can add vectors together and multiply them by real numbers called scalars. We will primarily focus on vectors that belong to the set of all ordered lists of real numbers with a specific number of components. Beautiful. That's beautiful. Because most algorithms in linear algebra are built around this type of vector. And this type of vector is ones that belong to the set of all ordered lists of real numbers with a specific number of components. In Chapter 8, we will see that data is often represented as vectors within this set of ordered lists of real numbers. In this book, we will focus on vector spaces that have a finite number of dimensions. When we work in these finite dimensional spaces, there is a one-to-one match between any kind of vector and the set of all ordered lists of real numbers with a certain number of components. Whenever it is helpful, we will rely on our understanding of geometric vectors and use algorithms based on arrays to perform calculations. Perfect. Okay, so moving on. One major idea in mathematics is the idea of closure. That is the question. This is the question, rather. What is the set of all things that can result from my proposed operations? In the case of vectors, what is the set of vectors that can result by starting with a small set of vectors and adding them to each other and scaling them? This results in vector space, section 2.4. The concept of a vector space and its properties underlie much of machine learning. The concepts introduced in this chapter are summarized in figure 2.2. This chapter is mostly based on the lecture notes and books by Drum and Wheel, 2001, Strang, 2003, Hogben, 2013, Lyson and Merriman, 2015, as well as Pavel Greenfield's Linear Algebra series. Other excellent resources are Gilbert Strang's Linear Algebra course at MIT and the Linear Algebra series by 3 Blue, 3 Brown. So we have those. I'll probably put these in the descriptions of this video, but you're gonna have to do this on your own. I might be doing this on my own. I'm always interested in optimizing my time spent consuming stuff, because like especially 3 Blue, 1 Brown, like there's a point where it's like, yeah, Mr. Beast, you might want to watch that because he's got explosions and turns it into like a gambling. But like, how much entertainment do you need ultimately? Like, these videos are beautifully animated. They have music. They have everything. So just like, swap this out for entertainment. It's probably it's not it's not nearly as entertaining as whatever's on Netflix or whatever influencer is trying to grab your attention. But honestly, I would say, why not? Like, do blinking, flashing lights really entertain you more than these concepts? Because this stuff is interesting, right? People have been working on this throughout humanity, and we're talking about like how things work. Like, how is that not interesting? How could that not be a form of entertainment? So linear algebra plays an important role in machine learning and general mathematics. The concepts introduced in this chapter are further explained to include the idea of geometry in chapter 3. In chapter 5, we will discuss vector calculus, where a principled knowledge of matrix operations is essential. In chapter 10, we will use projections, to be introduced in section 3.8 for dimensionality reduction with principal component analysis, PCA. In chapter 9, we will discuss linear regression, where linear algebra plays a central role for solving least squares problems. So here we have figure 2.2, a mind map of the concepts introduced in this chapter, along with where they are used in other parts of the book. So mind maps I've heard of a lot. A lot of people swear by them. I've never really used them, but I don't even have a bachelor's degree, let alone a master's or a PhD. So maybe I need to start using them. Okay, so we've got vectors. So composes, closure, property of. So a vector composes a matrix, which will be explored in chapter 5. A matrix represents a system of linear equations that are solved by Gaussian elimination and that solve matrix inverse. A matrix represents linear affine mapping. That will be covered in chapter 3 on analytic geometry and chapter 12 on classification. And that's what happens when a vector composes into a matrix, and we'll cover more of that later on. All right, so a vector also has a closure, and that's a vector space, and then group abelian with the plus sign, and chapter 12 we'll have more about that. And then a vector is a property of linear independence. There we go. So I'd like to make my own. I'd like to make my own mind map. So that's the other thing we'll probably do, is work with ChatGPT. Okay, so explain to me like the power of mind maps, and work with me to make it so that I create mind maps and I do it using like open source tools. Like if there's a Python mind map library or something like that I can use, because basically I want to further my education, and I am worried that if I don't use the most scientifically valid learning tools, then I will never be able to grasp the concepts at a high enough level to further my education to the way I desire. So, assign a letter grade to a mind map as a scientifically valid learning tool. Include it on like a tier list, like S tier, A tier, like a tier list, right? So sorry, there are some typos, but it should be clear given the context what I'm saying. I'm talking about a tier list. So there's like the S tier, there's the A tier, and so on. So I apologize if there's typos, but it should be clear what I'm saying here. So I want you to do that for me, and then for each scientifically valid tool in the tier list, I want you to provide me some free open source tools that I can use to implement them. All right, and with that, I will take a break. I'll be right back. All right, so I'm back. So, okay, perfect. So yeah, here we've got so the mind mapping is in the A tier. Yeah, it's really not in the S tier. Yeah. So really, what we want to be doing, the absolute gold standard, is we want to be doing Anki. And I don't even have it. I don't even have it pinned anymore. So, it's no wonder I've been kind of failing to further my certifications and education and all that. I don't even have Anki pinned to my quick launch anymore. So we'll pin it to the taskbar. It belongs front and center there. It's an essential tool. The next one is engaging with the material by self-testing. So we've got some tools for that. We've got Quizlet API. So here we go. We've got a tool here. Okay, well, I'm not sure how to use this. But active recall is definitely, so let's type in Python active recall tool. There we go, active recall planner. So this is probably a good one. Yeah, so clear the final references, documents, and background. Yeah, so we've got an algorithm here for active recall. So the algorithm, the first step is to scope the subject. So you need the syllabus, slides, book chapters. So you write down all words and topic that you do not know the meaning. You write down questions about the subject on a piece of paper, Cornell style. So a lot of yep. So,
okay, so the method is as
Ali
follows.
Abdul.
Basically, instead of ever writing any notes, instead of
I'm good with Ali Abdul. He's a bit of, he wants to sell you a lot of stuff, but okay, I'm good with that. So, and then yeah. So this is probably worth a watch for sure.
the order in which questions are asked.
Yeah. So this is worth a watch. Yeah, this is a good one. Oh, and looks like we got another one here. So we've got active recall planner. Now we've got just the yeah, okay. Okay. Yep. Okay, so these are good ones. I like it. All right, and then what else we got? So we got on the A tier we do have mind mapping, which mind mapping can encourage meaningful connections. It can aid in memory recall, and it can make you more creative and effective at brainstorming because all of the related ideas should be there as well, not just the main ideas. So okay, so we can use Obsidian. I think Obsidian's the free one. Yeah, Obsidian's the free one. So I've definitely tried using Obsidian before. I kind of don't like it, but I don't know how to use it. So yeah, Obsidian is free for personal use. So let's go with Obsidian. And then you can use Jupyter Notebooks for teaching notes. Yep. It's a good one. Okay. Okay, so we'll just focus on the SNA tier. So, mind mapping, summarization and note taking. So we definitely need Obsidian. We definitely need Anki, and then some sort of active recall tool. We'll probably need as well, and I guess we could use this tool here. This person wrote a tool for active recall, so we can dive in and try to figure out how to use that. We can also watch this video and see what he says about active recall. And it looks like he's got a tool here as well. He's got a spreadsheet. Yeah, so okay, so those are worth it. Later on, I'll probably leave this in the description. All right, so that brings me to dots 2.1, which, I mean, it's going to take a while to get through this book. There's just a lot here. So I'm typically good for an hour before it starts getting where it's just not getting in there. So if I do a Pomodoro and I take 5-15 minutes or whatever, I can do more. But as it is, I'm just doing this for my own interest casually. I'm not studying for coursework or anything like that. So I like to keep it, fun. If I'm really grinding myself to the ground doing 8 hours a day for nothing, I just don't see the sense in that. So that's going to be it for this video. Stay tuned for section 2.1.